Welcome back. This is the second video of section 4.4 in which we are going to continue our study of reflexive spaces. Before we continue, let me add a remark on kakutans theorem that we proved in the previous video. Weak compactness of the closed unit ball is equivalent to weak sequential compactness of the closed unit. And this is actually a deep theorem. Now, we'll prove that compactness implies sequential compactness in the next section once we study separable Banach spaces. Okay, and the converse is actually more difficult to prove and is known as the Eberlein-Smullyan theorem. Okay, we'll present a general result in section 4.6, but I'm not going to cover it in these presentations actually, but the proof is in the lecture notes. So it's an optional section because it's not part of your program, but you should know the result. Okay, it's a deep result actually in functional analysis. Okay, so therefore we have now 4 equivalent conditions. E is reflexive. The closed unit ball is weakly compact. This is just Kakutani theorem. Third condition, B is weakly sequentially compact, Eberlein-Smullyan. And fourth condition, every bounded sequence of E has a weakly convergent subsequence. And this is probably the most important application of reflexivity in analysis. Okay? Because in analysis, you deal a lot with sequences. So we should be able to extract from the sequence a subsequence which converges in some sense. Now, in general, as you know, if E is infinite dimensional, we cannot extract from a bounded sequence a strongly converged subsequence. But if the space is reflexive, we can extract a weakly convergent subsequence. Now, you may easily prove, and I suggest that you prove it actually, prove that 3 is equivalent to 4. Take a paper and a pen and prove that. Okay, and so what I'm saying here is not really trivial because we know that in a metric space, compactness is equivalent to sequential compactness. But we know that in infinite dimensions, the weak topology is not metrizable. So this result does not follow from the corresponding theorem that we proved in the metric topology course. Okay, so this is really something remarkable. Okay, so having said this, so in practice, you can use all these implications actually without proving them. Now let us illustrate the use of reflexivity in a minimization problem. Okay, suppose that E is a reflexive Banach space and consider a continuous function, strongly continuous function from the closed unit ball into R, which is convex. Then phi has a minimum value. This is not true without the assumption of reflexivity actually, because we can give counterexamples. So in order to prove that, I will divide the proof into 2 steps. In the first step, I will prove that phi is bounded from below. So there is an infimum. And the next step, I prove that the infimum is a minimum. Okay, so the infimum is achieved. Okay, so we reason by contradiction. What does it mean that phi is not bounded from below? Phi is not bounded from below means that there is a sequence in the domain of phi whose image tends to minus infinity. So in particular, so you can construct easily. If you negate the condition of boundedness from below, you will find a sequence xn whose image is less than minus n. Now, here we use reflexivity. Since xn is bounded or in the closed unit ball, then it has a convergent subsequence weakly. So we may still denote the subsequence, so there's subsequence here, by the same symbol in order to avoid subscripts. And this is what we usually do. So we may assume that xn converges weakly to some point A. Now, if you recall Mazur's lemma that we stated earlier, when xn converges weakly to a limit, then there exists a sequence in the convex hull of the range of the sequence that converges strongly to A. But actually, we can do better. We can take the sequence yn not only in the convex hull of x1, x2, etc., but we can take it on the convex hull of the set starting from xn, xn plus 1, etc. Okay, so this means that yn can be taken as a convex combination of the elements of the sequence starting from index n. Therefore, we can write yn as this convex combination. So we can write it as sigma of tin xi, where I varies in a finite subset of the index set n, n plus 1, etc. And the coefficients must be positive and sum to 1. Now, what does it mean that phi is convex? Phi is convex means that the image of a convex combination is less or equal to the convex combination of the images. So this is convexity. Now, by our condition, phi of xi is less or equal than minus I. So, and since tin are non-negative, can multiply and do the summation. But since I is in the set, so I is bigger or equal than n, then minus I is less or equal than minus n. So I can put the minus n outside the summation because it doesn't depend on I. And the tin sum to 1, so I just get minus n. Okay, so this means that phi of yn diverges to minus infinity. But this is a contradiction because phi is strongly continuous. So phi of yn must, and yn converges to a, so phi of yn must converge to phi of a. So this is a contradiction, and therefore phi is indeed bounded from below, and therefore it has an infimum. Okay, so this is the first step. So let m denote this infimum. We want to prove that this infimum is a minimum. Okay, so by a fundamental property of the infimum, there exists a subsequence xn in B, such that phi of xn converges to the infimum. Okay, it's a fundamental property. And by reflexivity, xn has a subsequence that, once again, we still denote by the same symbol, that converges weakly to some limit a in the closed unit ball. Okay, now pick an arbitrary positive number epsilon, and consider the set capital A sub epsilon, which is the set of all elements in the closed unit ball X, whose image under phi is less or equal than the infimum plus epsilon. Okay, so first of all, you may easily check that A epsilon is a convex set. This follows from convexity of phi. So just write the details. And continuity of phi implies that A epsilon is also strongly closed, because it's the inverse image of the closed interval minus infinity n plus epsilon under phi. But we know from the previous lemma that a strongly convex set, which is the convex set which is strongly closed, is weakly closed actually. So A epsilon is weakly closed. And therefore, since phi of xn converges to m, what does it mean, phi xn converges to m? It means that phi of xn is between m minus epsilon and m plus epsilon. So in particular, phi of xn is less or equal than m plus epsilon for n large enough, and therefore xn belongs to A epsilon. But xn converges weakly to small a. Therefore, the limit must be in the weak closure of A epsilon, which is just A epsilon, okay, because it's weakly closed. Therefore, phi of A is less or equal than m plus epsilon. But this is true for every epsilon. So therefore, phi of A is less or equal than the infimum. But phi of A is bigger or equal than the infimum. Therefore, we have equality. And therefore, the infimum is achieved at the point A. Okay. So this is a typical illustration of the use of reflexivity in analysis. Now, of course, so as we said, we need really the assumption of reflexivity, because otherwise there are many counterexams that may be given. And second remark, there are many other variants of this result. For example, instead of working on the closed unit ball, we can work on a convex closed set, which is bounded. And even we can work actually on the whole space, but we need to put an assumption actually that phi of x tends to infinity at infinity. Okay. And continuity of phi can be replaced by a weaker assumption that we call weak sequential lower swimming continuity. Okay. So all these things are studied and used in the calculus of variations, very important field of analysis. Okay, so let us end this section with two results on reflexive spaces. And I suggest that you prove them on your own as an exercise. So first of all, a closed subspace of a reflexive space is reflexive itself. And second, result, a Banach space is reflexive if and only if its dual is reflexive. So please try to take a paper and a pen and try to think of these problems and write the correct proof of them, and we'll solve them in the exercises. Okay. So this concludes this video and section 4.4. So thank you for your attention and see you next time.